okay, and what is the diameter of the dipole, and there is a gap here, for example, between these two, where we fed, the signal is fed from here. What is the gap here? Okay, these are the design parameters for the antenna. For the patch antenna, for example, dimensions of the patch, thickness, width, okay. For the reflector antenna, what is the kind of a reflector, okay, what is the curvature, what is the, we can say they are like a mechanical description for them, and what is the, most of them not electrical terms, okay, you describe physical system. So now we are in the wire dipole. This is wire dipole. Now, as I said, the system is implemented already. So here we write the frequency. For each antenna, there is an operating frequency or resonant frequency. The antenna cannot be used for all frequencies. In your house, you have Wi-Fi, and you have the router. All of us, you have the router. This router, okay, the current wave Wi-Fi is operated 2.4, the frequency 2.4 gig. So now, if you check the antenna in that router, you will find that antenna, okay, is designed to be operated at that frequency. If you take the antenna out and you connect it to another circuit, generates different frequencies, I say 1 gigahertz, it will not work, okay? So there is a specific frequency that is used for each antenna. At that frequency, actually, the antenna gives highest efficiency, okay? And we will see today some of these features, okay, guys? So what you do in your lab one, in the project one, sorry, and again, the project is individual, okay? We write here what is the frequency, and in the report, if you go to the report, it says to you, it's combination, they put it 2 plus, I think, the 4 digit of your UIN, your ID, or ID number, okay? So whatever your ID number, put it plus 2 and put it. Now I'm going to, let us say it is 2. Assume it is 2 gigahertz, just 2, okay? The frequency is 2. And now this will be computed later by the HFSS, okay, based on the frequency that we entered, which is 2. So when we go to the synthesis, okay, after that, after you enter the frequency, go to the synthesis, now the HFSS computes for you these parameters based on the 2. You will see this one, they will change. Okay, now these are the new values which are required if you want to design dipole, and this dipole will be used at 2 gigahertz. After that, go to finish, okay? Now we finish our project, and now the HFSS building the system, and on the right, left side, you will see here the system appears here, the structure. Okay, it takes a little bit time. Yeah, this is our antenna. This is our antenna. This is the rod. This is the dipole. This is the gap here, and the feeder here. Okay. And this is the structure that built it, okay, but now it is built already. But for you, you will do something like this, but not dipole. And you can do whatever you want. Later we will see. Now, this is our antenna. What you will do? First of all, after you design your antenna physically and you are done with it, in HFSS, we go to the this one here, simulation. You see this simulation. Okay, now in the simulation, we have, first you need to validate your design. You validate your design means the HFSS checks your design. If you did any mistake or if there is any problem, okay, you will be informed about that before you go to the next step, which is the analysis and the simulation. So first you go to the validate, and in the validate, Okay, we get this one. Okay, it says to you everything is correct. Is the design, the model, okay, the excitation, boundaries, okay, mesh analysis, setup, optimization, and the relation, everything is okay. If you do any mistake during your design, this design is already built and they built it, okay. Probably you will have, if you do your design, probably you will have something wrong, and then you go and check what is wrong in your system. Now our design is okay, you don't have problem with the design. We will go to the analyze. Analyze is the one which simulates and creates the results. Okay, as I said, the problem is solved by FEM, finite element method. They divide the space to the small elements, very small elements, and they solve the differential equation in that one computationally or numerically. It gives good result, but it has a lot of computation. So you go to the analyze, and here you will see the analyze here. Okay. Now we are starting. This is here. Okay, you can. This is the analysis. Take a little bit time, because as I said, it's not light software, and it's solved numerically. So after that, when the analysis is done, you will be able to see the result of analysis, and depends what do you want. For example, you want gain, okay, of the antenna. As I said, the antenna radiates. What is the antenna? The antenna is the last stage in the transmitter and first stage in the receiver. So you have electronic circuit in the transmitter. You have a signal. For your example, your phone. Your voice, okay, is the first step. Output of after my microphone is analog signal related to your voice. Then this analog signal will be filtered, cleaned, and then it will be converted to the digital signal, because the phone and the mobile system is a digital system. It will be cleaned again and filtered, and thousands of operations, okay, and algorithms. There are a lot of algorithms, okay, are performed on this: coding, error correction, error detection. At the end, at the last end, you will get the signal that you want to send it to the receiver, and from this signal, the receiver, the other terminal, okay, can understand the message or what you say. So what we have now, this signal, the last signal in your electronic circuit cannot propagate in the atmosphere, or if you have, for example, waveguide, or if you have coaxial cable, you can't send electric signal. If you have what we call it, fiber optics. So what you have, you need to convert the electric signal to the electromagnetic signal, and this electromagnetic signal can propagate. And this is the task of the antenna. Antenna converts the electric signal, which you created in your electronics, okay, and will be the electric signal will be converted to the electromagnetic signal, and this electromagnetic signal, okay, has the ability to propagate to the other terminal or to the receiver, okay. Again, this is not easy job, and the propagation itself is not easy job. A lot of math and a lot of calculations we have with it, okay. So the antenna now, the antenna you use it, we need to know the gain of the antenna, and the gain of the antenna is depends on the direction. Some antennas propagate in the gain of the antenna, okay, is very large or very high gain in one side and small in other sides. So we need to use that one, which is called the radiation pattern. Some antennas has almost same gain around it. Actually, we don't have antenna transmit like equal gain like a wall around it. Only this is theoretical antenna, which is called isotropic antenna. Okay, in the practical, we don't have, practically we don't have this antenna. We have antenna which is like a dipole today. The radiation pattern, you will see it, it's similar to the isotropic, but it's not isotropic. You can say it's like a donut shape. Okay, so now the simulation is done. Okay, and okay, we now this is the antenna, our antenna. We will go here. This one is done. You see here we have result. On the left side, you have result. In the result, okay, you will have all the results that are available, or you can get it from the simulation. For example, it's required from you to find the 3D, I guess, 3D gain. This is the 3D gain, okay, FF 3D gain total. This one here, okay, double click, and you get it, this one. This is the gain of the antenna, okay. Usually it's normalized, okay, but you can see from the gain, this one, it's look like a ball, but it is not a ball. We have here, this is the axis where the antenna is, okay, and we have here weak radiation. The radiation here almost zero, okay. You can, this one is required from you, okay. So when you want to record it, just right click, and you can use export, and after that, from here you can use whatever you want as image, JPG, for example, and save it. You need to include something like this in your report. Okay, if you want to rotate this, go to this one here, rotate, and in the rotate, you need to specify you want to rotate it around the center, you want to rotate it around the axis, or around the cursor. Let us say around the axis. I'm going to rotate it here. Okay, this is the antenna. It's not a ball, okay, because the ball is ideal radiation pattern for the isotropic antenna, which is also ideal antenna. We don't have isotropic antenna, but we use it to compare our result with it. And this one here, the antenna, radiation pattern of the antenna here, this is in phi, this is 0, the phi is 0, this is the theta, okay, and here you have the color map. Based on this color map, you know the radiation power, okay. The red one here, it's 10, and then here this area, which is almost the weakest area, and the yellow or green area. Now this is a 3D. This is a 3D, okay, 3D gain for your radiation pattern, okay. If you change it like this and you want it back, okay, go to the orientation, and from the orientation choose isometric, okay, it comes to you again in the original shape. Now, this is what you need to include in your report based on the result, on your ID, okay, because the frequency, you use it, you should use your frequency, and the frequency is different, okay, which is 2 plus your ID number. Remember, our antenna, we put 2 gigahertz, okay. Now suppose I want radiation pattern. Let me show you here. If you see, I want the radiation pattern. Usually this is useful, but usually we prefer it 2 dimension. So I wanted 2 dimension in this plane. You see this plane, this is this circle here, this one, okay, this circle, okay, corresponds to phi equal 90, And then theta in this plane, where we have phi equal 90, theta will change from 0 to 2 pi, 360. And we will see it again in this plane. We see this circle here, okay? So this is 2D again. This is a 3D, but we want 2D, this one here. Go to the result. This is a 3D, this is 2D, okay? So this is 2D. Here, whatever you want, okay, for us. Now let us close this. Now we want, for example, this is a gain. Now this is the gain, okay, when, look here, when phi equal 90 degree and the frequency 2 gigahertz. And why we did this? We have this because we have different theta, okay, which is the angle from the vertical axis, okay, going down here. For example, if I wanted at phi equal 90, this is 90. For theta equal, for example, 60 here, the gain of the antenna here. So if you put it in this orientation, this is the gain. So as I said, the gain depends on the direction, and the maximum gain for the dipole, this kind of antenna, the maximum gain is in the direction perpendicular to the dipole. This is a dipole, okay, here, okay, here. This is the maximum gain here, okay. So direction should be perpendicular to the center of a dipole here. This is the other one, okay. I think this one is not required from you in your report, but just I want to show you later, probably will need it. And again, what you want, just go to export, and from export, and you can save it as an image, or if you want to Excel file, CSV, okay, or image. What else we need? Return loss here. This one. This is, I guess, one of your question in the part one wants you to find the return loss. What is the return loss for each antenna? As I said, the antenna is designed to be operated at a certain frequency. So at that frequency, okay, the efficiency of the antenna is very high. And when the efficiency of the antenna is very high, we say, in other words, the return loss is very low. Return loss is you can consider it like the amount of the power that is transmitted by the antenna, okay, with respect to the power reflected back to the source by the antenna. If you use a frequency different than the frequency that the antenna is designed, for example, now we have 2 gigahertz. If you feed it by 1 gigahertz antenna and it is designed for 2 gigahertz, then the antenna will have a lot of power transmitted back, reflected to the system. And return loss, that's mean when you convert it to the ratio, it will be 1. That means the power transmitted equal to power reflected, and this is the worst case. So this is also return loss. It's required from you, okay? And you need to include it in your report.
So,
yes.
So in the project, they want us to calculate the minimum return loss?
No. There is no, this one, part one, there is no calculation. Just put the simulation, and you can say, I designed my antenna, for example, for 2 gigahertz, and it's clear from this figure, okay, the minimum return loss is obtained at that frequency, okay?
They want the value in dB, you know, like the y-axis, and they want it to 2 decimals. So they told us to zoom in or something like that to calculate it accurately, but I still don't know how to do it.
Just to find it, you can't zoom it and to find the value, and you can't put it in your report. put whatever the value of the return loss at the frequency where your return has minimum, or provide 4 significant digits. Yeah, for the, yeah, write your, exactly this figure here, what we have it here. Okay, and keep until you find whatever you want. Okay?
Yes, I still don't know how to find it.
How you find the value, you mean?
The minimum, yeah, the minimum loss.
If you right click on the curve info box, there's a trace menu that comes up, and then you can set the trace characteristic to minimum, and it'll display it.
Oh, the trace characteristics? Okay, thank you.
And keep in your mind, you have to include also this one in your report. Okay? And yeah, this one here. This one. Later you will be also able to see more data. For example, let us see the electric field, for example, on the antenna itself. So we go to the, okay, here, go to the field. For example, I want electric field as a vector, electric field, all objects. Now here, this is the electric field of the antenna. You see it here. This is the electric field, radiated electric field. And yeah, you can change it. Okay, so what I'm going to do, I will change the scale. Okay, instead of automatic, I will put it limit. I will put it linear, and minimum, I will put the minimum 0, and maximum, it's in the blue area, most of them, so it's 250. Let us say maximum 300. Okay? So now you see it's more clear, the radiation pattern. Sorry, electric field radiated from the antenna. And if you see it, look like here, look, it's like has a geometric like shape like this. Okay, you see it like a square here, and if you keep it, so it is like cube. And actually, this is what you do it in the when you simulate any system in the HFSS. After you done with your simulation, you need to put your design inside a box. They call it a radiation box, and the simulation, as I said, it's solved numerically. So the problem will be solved in that box. So this is the what we have here inside. This is the radiation box. Actually, that they use it and put this antenna inside it. So the solution will be inside that box. Okay, not everywhere. Okay, so this is because the radiation box. Okay, and this is the electric field. And if you see, they give you the direction of the electric field, how the electric field radiated or organized. Okay, so now the electric field. Now the electric field for this antenna. If you want magnetic field, also you can get the magnetic field. Again, you go to the plot field and choose H in this case. Vector H, because I have here this one, I have to delete it, and also I have to select the object. When you sketch this one, you need to select the object. So I wanted this one, the object, okay? And then I go to this field. This one is not, I guess, not required from you to sketch it. This is the magnetic field. It's not required, but later you will need it in your project. Okay? So in your project, you just need to do the magnetic field, the gain, I guess, and the return loss. And design not design, actually enter the frequency based on your ID. Okay? And take the measurement. So now I want you to go and start working your project if you want.